All right, let's talk about something we all use constantly in Java, sorting. Today, we're going to pull back the curtain on what's really happening inside those powerful built-in methods you use every day. Let's dive right in.
You've probably typed this line of code 1,000 times, right? You hand Java an array, you call .sort, and poof, it comes back in perfect order. But what's actually going on in that black box? It's definitely not just one simple algorithm.
See, the Java Development Kit is actually really smart. It knows that not all data is the same. So under the hood, it makes a critical choice for you. It picks between two different highly optimized sorting engines, one that's built for raw, blistering speed, and another one that's designed for being careful, predictable, and stable.
So, let's meet these two workhorses. Understanding them is really the key to mastering how sorting works in Java.
The easiest way to think about it is like this. For the simple stuff, primitive data types like integers, Java unleashes dual pivot quicksort. It's a total speed demon. But for more complex things like objects, where the original order might actually matter, it switches gears to tim-sort, the intelligent, stable workhorse. Dual pivot quicksort is the default for primitive arrays because it is just incredibly fast. It operates directly on the data. But there's a really important trade-off. See that word unstable? What that means is if you have two equal elements, say two 7s in your array, there's no promise they'll stay in their original relative order after the sort. For just plain numbers, that's usually not a big deal.
And then, on the other hand, we have tim-sort. This is a super clever hybrid algorithm that's used for objects, and its superpower is stability. So imagine you have a list of employees, and it's already sorted by name. If you then sort that list by department, stability guarantees that within each department, the employees are still sorted by name. It also guarantees consistent performance, which is absolutely crucial when you're dealing with complex data.
And this system wasn't just built overnight. It's evolved over time. Before Java 7, a more classic quicksort was used. Then, Java 7 brought in the faster dual pivot version we just talked about. And with Java 8, we got parallel sorting, which is designed to harness the power of all those modern multi-core processors for gigantic data sets.
Okay, so the theory is great, but how do we actually apply it? How does this help you write better code? Let's build a quick, practical guide for choosing the right sorting method for your specific job. This table right here, this is basically the whole explainer in a nutshell. Look closely. For a primitive int array, you get the fast but unstable quicksort. For an object array or a list, you get the stable tim-sort. Now notice tim-sort's worst-case time, it's still a solid O of n log n. Quicksort, on the other hand, can degrade to O of n squared, which is way slower, even though that's pretty rare in practice. And parallel sort, that's a whole different animal, really designed for massive scale.
This is always your starting point. The type of data you're sorting fundamentally decides which algorithm Java is going to use and what kind of performance you can expect. This slide just hammers that point home. Sorting a primitive int array is all about raw speed. But the moment you switch to an integer object array, two things happen. Java switches to the stable tim-sort, and it introduces something called boxing overhead, which can make your sort a lot slower. The key takeaway is simple. If performance is absolutely critical when you're sorting numbers, you have to stick with primitives. So this brings us to that big concept of stability. You have to ask yourself, if two items are considered equal by my sorting rules, do I need them to stay in the same order they started in? And if the answer to that question is yes, well then your choice is already made for you. You must use a sort that works on objects, because only those methods guarantee you'll get the stable tim-sort algorithm. For a lot of data processing tasks, this is totally non-negotiable.
So what about that parallel sort we mentioned earlier? It sounds cool, right? Using all your CPU cores? Well, don't just reach for it on a whim. The overhead of managing all those threads is pretty significant. As a general rule of thumb, you should only really consider Arrays.sort when you're dealing with huge arrays. I'm talking over 1 million elements, and you're on a machine that actually has multiple cores to throw at the problem.
All right, let's level up. Knowing the basics is good, but avoiding the common mistakes, well, that's what separates a good developer from a great one. So here's some rapid-fire tips. You got to watch out for these. Trying to sort an array with nulls in it? That'll crash your program. A poorly written comparator? That can lead to complete chaos. We already hit on boxing overhead pretty hard. And please, never ever modify a list while some other thread is trying to sort it. Oh, and sorting a linked list directly? It's really inefficient, because behind the scenes, Java has to convert it to an array first.
So, how do you take all this knowledge and use it to sound like an absolute expert in a technical interview? Let's break down the perfect answer.
Imagine the interviewer asks you about the complexity of Arrays.sort. This right here is your golden answer. It's concise, it's accurate, and it proves you understand the really important differences for both primitives and objects, including the worst-case scenarios and that all-important concept of stability. Here's a simple, three-step framework you can just memorize. First, name the algorithms. Second, state their key properties, their complexity, and their stability. And third, explain the practical reason why you choose one over the other. A structured answer like this shows you really get it.
And that's really what this is all about. It's about moving beyond just knowing the syntax of Arrays.sort to truly understanding the intelligent design choices that power it. Now you know it's happening under the hood, and you can make much smarter decisions in your own code.
So we've pretty much mastered how Java sorts, but this all leads to a much bigger question for any programmer. Just because you can sort something, does that mean you should? When might a hash map, or maybe a heap, or a totally different data structure be a much more efficient solution to your problem? That's a thought to take with you. Thanks for joining me.